Imagine this. You're controlling a complex humanoid robot, but not just making it walk straight. You're guiding it for tricky stuff. Maybe picking up something delicate off the floor or navigating a winding path, maybe even mimicking some, complex movements.
Right.
It's almost like the robot becomes a physical extension of yourself, even if it's miles away.
That sounds, well, pretty futuristic, doesn't it? Because, yeah, we have humanoid robots, but getting them to do those kinds of precise, coordinated things reliably in the real world, especially over distance, that's been really, really hard.
Totally. And the source material we've got here really spells out why. There seem to be two really big challenges that keep popping up in humanoid teleoperation.
Absolutely. The first one is just how difficult it is to coordinate the whole body, arms, legs, torso, getting it all to work together smoothly like a person does without thinking. A lot of systems, they just can't quite manage that full body harmony.
Okay, so full body coordination is one major hurdle. What's the second big headache?
Drift. It's kind of like your robot slowly getting lost.
Lost.
Yeah, because tracking exactly where a complex-legged robot is in the world is surprisingly hard. So small errors creep in with every step, every little movement. And over time, or over distance, those errors just pile up. The robot drifts, sometimes significantly, of course, and that makes any kind of precise task or, long-distance navigation basically impossible.
Okay, so lack of coordination and this kind of crippling drift over distance, that sets the stage perfectly for what we're diving into today. Clone.
Right.
We have the research paper right here just describing this new system, Clone, and it's designed specifically to tackle those exact problems. So our mission today is to really unpack Clone, understand how it's different, and figure out what it means for actually making humanoids useful as, like, remote avatars.
Sounds good. Let's dive in.
Okay, so let's start by digging a bit deeper into those problems with current systems based on what the sources say. You mentioned coordination first.
Yeah. So a key limitation the papers point out is how existing methods often handle the robot's movement. Sometimes they treat the upper body and the lower body almost separately.
Like two different control problems.
Kind of, yeah.
Yeah.
Controlling them somewhat independently. Or even if they try for whole body control, they often get really focused on just stability, just keeping the robot upright.
Okay.
Which sounds good, but it means they often sacrifice the robot's full range of motion.
So it can maybe stay standing, but it can't do, say, a smooth, deep squat while it's also reaching for something precisely.
Exactly that. It prevents those really complex fluid movements that humans do naturally, where everything just works together. And critically, for anything involving, using the hands, picking things up, putting them down, many older approaches just don't pay enough attention to crucial details, like the exact orientation of the robot's hands or wrists.
Right, so it's not just about not falling over, it's about the actual quality and coordination of the movement itself, especially when you need dexterity.
Precisely.
Okay, what about that drift problem again? Why is it so tough to keep track of where a humanoid is accurately over a distance?
Well, a lot of that comes down to how many systems operate in what's called an open loop way.
Open loop.
Yeah, imagine telling the robot, okay, walk forward 10 steps, but then never actually checking if it did move 10 steps forward relative to where it started in the world.
Like shouting instructions into the void without getting any feedback.
Exactly. And for humanoids, this is particularly tricky. Their legs interacting with the ground, it's complex. Plus, they have so many joints, estimating their exact global position just from internal sensors is really difficult. So tiny errors in estimating, say, movement direction or distance just add up, step after step after step.
It's like if you close your eyes and try to walk a straight line, you inevitably veer off course.
Yeah, perfect analogy. And for a robot, that subtle veering turns into significant drift over, dozens or hundreds of steps. You might tell it to go pick something up at coordinate X, Y, but by the time the robot actually gets there, it's really at X plus some error, Y plus some error.
Totally throwing off the task.
Completely. Makes precise interaction impossible. And just to add to the problems, many of the older ways of doing teleoperation relied on these really bulky, expensive motion capture setups.
Right, like in a movie studio.
Yeah, which are just not practical for deploying a robot out in the real world, outside of a controlled lab environment.
Okay, so the picture is awkward, uncoordinated movement, maybe ignoring key details like hand pose, this really damaging drift over distance because of open loop control, and often needing complex setups. So how does Clone try to break through all this? The
Well,
source material points to three key innovations working together.
yeah, and this is where it gets really interesting because they're not just patching one problem, they seem to be rethinking the whole approach. Their first big idea tackles that coordination issue. They use something called a mixture of experts policy, or MOE.
Mixture of experts. It sounds complex, but the idea behind it is actually quite neat, isn't it?
It really is. Think of it like assembling a team of specialists. Instead of one single general control policy trying to be good at absolutely everything, walking, squatting, reaching, balancing, all of it.
Which is maybe too much for one policy.
Potentially, yeah. So the MOE system has multiple smaller expert networks. Each one is trained to be especially good at certain types of motion or controlling specific parts of the robot's action space.
So maybe like one expert handles leg movements for walking, another is good at fine arm control. Is it that literal?
It's a bit more nuanced than that, but that's the basic idea. The system learns to dynamically activate and combine these experts based on what the operator is actually doing and the robot's current situation. And this allows a single unified control policy built from these experts to pull off really coordinated movements. Movements that blend locomotion and manipulation smoothly. It learns to use the robot's entire body effectively.
Unlike those older methods that might have simplified things.
Exactly, or some mocap approaches that might constrain movement. The source gives examples like coordinating the robot to pick up an object from the ground or carefully placing it in a bin some distance away, tasks that absolutely need that total body harmony.
Okay, so the MOE policy gives it the skill for coordinated whole body movement. That's huge. But that doesn't fix the drift problem on its own, right?
No, it doesn't. And that's where innovation number 2 comes in. Closed-loop error correction.
Cool.
This is the system's way of staying, anchored to reality.
The feedback loop we were missing before.
Exactly. Clone is constantly checking.
Wow.
Where is the robot actually in the world right now? And it compares that to where the operator intends the robot to be.
How does it know where the robot is?
It uses high-precision LiDAR odometry. Think of it like using laser scanning plus motion sensors to build a map and track its position within it. They specifically mention using an algorithm called FASTI-IO2,
Okay.
which is known for being pretty accurate and fast, even when things get complicated.
So LiDAR tells the robot its own position. How does it know where the operator wants it to be, or where the operator is relative to the robot?
So that's part of the elegance of the interface. It just uses the tracking data straight from a standard VR headset, something like the Apple Vision Pro was mentioned.
So the headset tracks the operator in their space.
Right. The system gets the operator's global position from the headset's tracking.
Yeah.
Then, crucially, it calculates the error between the operator's intended position, represented by their headset, and the robot's actual position from the LiDAR.
And it uses that different signal to constantly nudge the robot back on course.
Precisely. It's this continuous correction loop. It actively fights against that accumulation of small errors, effectively eliminating the drift problem. And the real beauty here is how simple the input is for the operator. They're just wearing the VR headset. The system only needs the 60 poses, so position and orientation of their head and their wrists.
Just 3 track points, head and 2 hands.
Yep. Just those 3 points from the VR gear are enough to drive this complex, corrected, whole-body movement of the humanoid.
That is remarkably lean input for such sophisticated output. Okay, so we've got coordination via MOE, drift correction using this closed-loop feedback. What's the third leg of the stool?
It's the foundation, really.
Right.
Robust training data. You can't train a system this capable without teaching it how to handle a huge variety of movements and situations. So the Clone team created their own specialized data set. They call it Cloned.
Cloned, okay. Why couldn't they just use, existing human motion capture libraries? There are massive ones out there, aren't there?
There are, yeah. The sources explain that while data sets like, say, AMAS exist, they were often captured for things like animation or virtual characters. They don't always capture the specific nuances, the physical constraints of a real robot, or the detailed ground contact interactions you need to train a truly robust robot controller, one that can actually perform tasks in the messy real world.
Mm.
And importantly, they often lack detailed, consistent data on things like specific hand orientations during manipulation tasks.
Right. The animation might look fine, But the robot needs to know exactly how to position its gripper.
Precisely. So they needed data specifically geared towards teaching a physical robot to do these things robustly.
So they built Cloned. What's different about it?
Well, they took existing data but then significantly augmented it. They used techniques like motion editing to create more diverse examples, filling in gaps. They also captured their own custom motion sequences, focusing on things like smooth transitions between different actions and really emphasizing those precise upper body and hand movements crucial for manipulation.
Yeah.
And critically, they systematically added that detailed hand orientation data throughout.
Because if you want to grab something, the hand has to be oriented just so.
Absolutely. And having this really comprehensive data set is key. It helps make the robot controller more generalizable, more robust, so it can handle not just the exact movements it saw during training, but also slightly different or maybe even novel movements from the operator.
Makes sense. How do they actually use this data for training?
They use a few clever techniques. One is a teacher-student approach. A more complex teacher policy is trained on perfect simulation data, and then it guides the training of a simpler student policy that's efficient enough to actually run on the robot's hardware.
Okay.
And they deliberately added noise during the student's training. For instance, adding velocity-dependent noise to the operator's head position signal
Why do that?
to mimic the real world. Real sensor tracking isn't perfect. It gets a bit jittery, especially when you move quickly. Training with this noise makes the final policy much more resilient to those real-world imperfections. Yeah, and they also use specific reward functions during training, like something called an AMP reward, which encourages the robot to maintain natural-looking, stable lower body movements implicitly without the operator needing to constantly micromanage its balance.
So, putting it all together.
Mm-hmm.
A clever policy architecture with MOE, real-time position correction with that closed loop, and a purpose-built, toughened-up training data set. That sounds like the clone recipe,
That's pretty much it.
but, the proof is in the pudding.
Yeah.
How well does this recipe actually work? What did the experiments show?
Right, they definitely put it through its paces, both in simulation using Isaac Gym, which is a pretty respected physics simulator,
Okay.
and then crucially on a real physical robot, the Unitree G1 Humanoid.
Simulation's one thing, but yeah, the real world is the acid test. What were some of the standout results?
Well, first, in simulation, they tested it against various reference motions. Clone consistently showed better accuracy in tracking those desired movements compared to the baseline methods they tested against.
So fundamentally better motion tracking.
Yeah, it helped validate that both their MOE architecture and that special clone dataset were actually leading to better motion reproduction quality.
What about those really challenging postures, like squatting low?
Ah, yes. They specifically tested performance at different heights, from standing tall around 1.2 meters all the way down to a really deep squat at 0.6 meters, which, as you can imagine, is notoriously difficult for humanoids to control stably.
Yeah, I could barely do a smooth, deep squat myself sometimes.
Right, so for a robot, it's a serious test. And they found something quite interesting here. Well, yeah, all the methods struggled a bit more in the deepest squat position.
Understandable.
Clone showed this notable tendency. It often seemed to prioritize getting the posture correct, meaning getting the arms, legs, torso, hands into the right positions relative to each other, what they call local fidelity.
Yeah.
It prioritized that, even if its absolute position in the world, the global error, was maybe slightly higher than some other methods in those really deep squats.
Interesting trade-off.
It suggests the policy is effectively saying, okay, this whole body configuration is complex and important, especially for manipulation, so I'm going to nail that, even if I'm off by an inch globally.
So it's like, maybe I'm not perfectly centered in the room right now, but I am nailing this tricky squat posture and getting my hand exactly where it needs to be relative to my body to grab that thing.
That's a great way to put it. It's focusing on the harder part, arguably. But the real excitement, I think, comes from the demos on the actual Unitree G1 robot.
Okay, what could it actually do in the real world?
So the sources describe really successful real-time teleoperation across a pretty wide range of skills. Arm waving, sure, but also doing those deep squats, standing up smoothly, navigating around, and quite remarkably, jumping.
Wait, hold on. You can teleoperate a humanoid robot to actually jump, just using head and wrist tracking from a VR headset.
The source material confirms it, yeah. They explicitly highlight that being able to execute dynamic skills like jumping in real-time teleoperation like this is a pretty significant step forward. It shows a high level of whole-body motion control fidelity.
That is genuinely impressive. Okay, and what about the drift? Did the closed-loop system actually fix that dreaded drift problem over distance in the real world?
They tested that very specifically. They ran a controlled experiment where the operator walked the robot along a path about 8.9 meters long.
Okay, nearly 9 meters.
And the quantitative results they report are pretty clear. A mean positional error of just 5.1 centimeters.
Wow, like 2 inches on average?
Yeah, and a maximum error over that whole path of only 12.0 centimeters.
So less than half a foot max error over almost 30 feet of walking. That sounds like a massive improvement over typical open-loop drift.
It absolutely is. It really validates that their closed-loop correction approach is working as intended in the real world.
Did they try anything longer?
They did. They also tested it on a longer, more complex path, 15 meters this time. It included things like turns, sidestepping, and then returning back to the starting point.
More like a real navigation test.
Exactly. And the robot apparently tracked the operator successfully throughout that whole path and came back to the origin with, again, minimal drift. It demonstrates the system is robust enough for these longer, more involved tasks in, less structured spaces.
Okay, so simulation shows the core ideas are solid.
Yeah.
Real-world tests confirm it can do complex movements, even dynamic ones like jumping. And crucially, it seems to have really conquered that notorious drift problem over significant distances.
It's a really powerful combination of features.
So let's zoom out a bit. Bringing this all together, why does this deep dive into clone actually matter for, the bigger picture of robotics?
Well, I think what Clone demonstrates is a way to overcome some of these really fundamental barriers that have, frankly, kept humanoids from being truly practical for complex remote tasks, enabling this kind of coordinated whole-body control and eliminating drift over distance, especially using such a relatively simple, non-intrusive control interface, just the VR headset.
Yeah.
That's a big deal.
It really feels like it bridges the gap between, simple human intention and complex robot execution much more effectively.
I think so. And this really opens up the potential for using humanoids in real-world scenarios that need both complex physical interaction and the ability to navigate larger spaces.
Like what kinds of scenarios?
Oh, think about inspection tasks in complex environments, maybe some forms of assembly, manipulation in places that are hazardous or just too far away for a person to be. Maybe even basic assistance tasks around a home or workplace that involve moving around quite a bit and interacting with different objects.
And the source also mentioned it helps with collecting data.
Yes, that's another key point. Because Keylone lets operators teleoperate such a wide range of complex, natural-looking behaviors so accurately, it becomes this fantastic tool for generating high-quality, diverse training data.
Data to train other robots.
Exactly. This data is like gold for training future, potentially more autonomous policies for humanoids. It creates this kind of positive feedback loop. Better teleoperation tools lead to better training data, which leads to more capable autonomous robots down the line.
That makes a lot of sense. Better tools make better data, make better robots. Of course, no system is ever perfect. What limitations does the source material acknowledge for Clone?
Yeah, they are quite upfront about a couple of things. One challenge actually relates back to that minimal input, just the head and wrists.
Which we said was an advantage.
It is for intuition and ease of use. But the flip side is, relying primarily on just those few control points can make it tricky to guarantee absolute fine-grained stability in every single possible situation, especially if there are highly dynamic or unexpected disturbances. Even with training tricks like that adversarial reward to encourage stability implicitly, there's probably a bit of a trade-off between the simplicity for the operator and achieving perfect, robust stability in the absolute most extreme edge cases.
Okay, so a trade-off between ease of use and maybe ultimate stability limits. What else?
The second main limitation they mention is related to very dynamic motions. So while Clone can handle things like jumping, which is already impressive,
Yeah.
the sources note that its performance does start to degrade for extremely dynamic movements. Think, really acrobatic leaps or maybe continuous single-leg hopping, that kind of thing.
Like robot parkour is still out of reach.
Pretty much, yeah.
That's-
The really challenging high dynamic stuff, they indicate that pushing into those regimes would likely require even more specialized training data that actually captures those extreme movements, and potentially developing control methods specifically tuned for maintaining balance during those really intense, fast maneuvers.
Okay, so highly capable for complex, coordinated tasks over distance, handles moderate dynamics like jumping surprisingly well, but the robot gymnastics team tryouts are probably still a ways off.
That sums it up pretty well, I think.
All right, so we've taken this deep dive into the source material on Clone. We've seen how it really takes aim at those core frustrations in humanoid teleoperation, that lack of full-body coordination, and that crippling positional drift.
Hmm.
It tackles these using that smart mixture of experts policy, the clever closed-loop error correction with LiDAR and VR tracking, and that specially curated, robust cloned dataset.
Yeah, the whole package.
And the experiments, especially those real-world tests on the Unitree G1, they really seem to confirm that these solutions work. They enable the robot to perform complex skills, even jumping, and crucially, maintain really impressive positional accuracy over significant distances.
It definitely feels like a tangible step forward, moving towards making humanoids truly functional as remote physical avatars.
Absolutely. Which leaves us and leaves you with this thought to maybe chew on. What really happens, what new possibilities open up, when a humanoid robot can reliably act as that physical avatar? Capable of complex, coordinated movements, navigating real distances with minimal drift, all controlled just by the subtle movements of your head and hands. Think about the applications that could unlock enabling human presence and physical capability in places we simply can't be, whether that's assisting in dangerous zones, exploring remote locations, or maybe just extending human reach and ability in ways we haven't even fully imagined yet. It really does feel like that science fiction future is arriving, maybe one coordinated step and one corrected centimeter at a time.